So we went over how to integrate over rectangular regions. So now we want to branch out into some more general regions. So this is kind of like what we did with optimization, where we started by optimizing on a rectangular region, and then we looked at a few different regions, and from there you can kind of get your footing and kind of see what the process is like, and then use that to move into pretty much any region, right, that we could describe. Obviously, you could get some really tricky ones in there, but for the most part, the techniques from one region kind of translates over to the next. So this is the example I want to start with here. Okay, so we want to do the double integral of x squared e to the xy, where d is the triangle with the vertices 0, 0, 2, 1, and 0, 1. So as usual, we want to start by drawing this out. Okay, so I'll go ahead. We'll make the scale a little bit large here. So we'll say that's 1, that's 2, that's 1. So we're not squished in there. So 0, 1, 0, 0, and 2, 1. Okay. So this is the region that we're looking at then. Okay. So before we look at exactly how to tackle this, I want to move back to the rectangular regions first to look at exactly what we were doing. So I drew this picture out already, but I just want to kind of describe what we were doing here. So on this one, we were integrating from 0 to 3 on the x's and 0 to 3 on the y's, right? So in the last video, we were kind of just thinking of it as going from the first x value to the last, and then going from the first y value to the last. I think it's a little bit better now to think about it as going from different lines. So we went from the line x equals 0 to x equals 3, and then we went from the line y equals 0 to y equals 3. Okay, that'll translate a little bit better over here, because notice we don't have a line that's just line on the axis anymore. We have a diagonal line. So it's not going to be just defined by a constant. We're going to have a variable in here. Okay, so let's start by writing down what each of these lines are. So this one, of course, is just y equals 1, and this one is x equals 0. Now this one is a straight line, so we can use the 2 points it goes through, namely 0, 0, and 2, 1, to actually find out what that line is, right? So the y-intercept is 0, so the b term. And then we can just plug in 2, 1 to see what the slope is. So we get 1 is equal to m times 2, so that means m is equal to 1/2, right? So that means we're on the line y equals 1/2 x. Okay. So we can't just integrate from 0 to 1 on the y side, because what that would do is it would give us this entire rectangular region here. Okay. The y points are going from 1/2 x to 1, right? So it's not, at this point in particular, on this, at the very edge of it, it's going from 0 to 1. But then at 1, for example, it's going from 1/2 to 1, and etc., right? So we need to take that into account here. So we're going to need to integrate from the line y equals 1/2 x to the line y equals 1 for this function, starting with the dy, right? Now we don't normally write like y equals on here. I'm just writing it out just to show you exactly what it's referring to. So you could just write just 1 up here and just 1/2 x down here, and that's fine, right? And then now that we've already restricted ourselves to this region, right? So we've kind of already squished this region so that it's only going to be going between 1/2 x and 1. Now for the x coordinates, we don't need to worry about that anymore. Now we can just go from 0 to 2, because the fact that we already cut this region off is going to keep us inside those lines. Okay, so what that's hinting at is that if we were to do the x part first, it's going to look a bit different. So we can't just interchange the bounds and be done with it, because if we did that, it would be kind of weird. What would happen is we would get this entire rectangle. We would go from 0 to 2, and we get all this part down here too. And then when we did the y part, we would only get this part right here. So we would have, mathematically what we would have is, we wouldn't even have a real answer. We would have our answer would still have x in it, which it shouldn't if we're doing a definite integral, right? If we're doing a definite integral, it should just be a number at the end. So it's not going to lead to the right thing. We can interchange the bounds, but then we have to change exactly the way we're doing it. So let's do it this way first, and then we'll look at what happens when we change the bounds. Okay. So this one right here, first we're going to integrate with respect to y. So x is going to be a constant here, right? So this is going to be 0, 2, and then we're just going to have x, and then, I'm sorry, that should be x squared, right? And then if we're integrating e to the xy, x is just a constant here, so this is going to be 1 over x e to the xy, which you can see just with a u sub, but we've done that form plenty of times at this point, right? So this is going from, y equals 1/2 x to y equals 1. And then we're going to integrate with respect to x. So when we plug in these points here, we're going to get, and this will cancel out, by the way, right? So we're just going to have x here. So we're going to get x times e to the x, because we plug in 1 for y, minus e to the 1/2 x squared, okay, dx. So we'll break this up into two integrals. 0 to 2 e to x e to the x minus 0 to 2 of x e to the 1/2 x squared dx. Okay. So the left hand one is going to require an integration by parts. The right hand one will just require u substitution, right? That x e to the x squared can be hard to integrate, but because we have the x out here, it'll just be taken care of by a u sub. So nothing to worry about there. So I'll just go ahead and do the antiderivative separately here. And then we'll deal with the bounds later. This is usually how I like to do it. So u equals x, so du is equal to dx. And we've done this one, of course, but it's always good to see it again, I'm sure. So vu is equal to e to the x. So this is going to be equal to u times v, so x e to the x, minus v du, e to the x dx. Okay, which is going to be x e to the x minus e to the x. And now we do the same thing with x e to the 1/2 x squared dx. This time we're going to let u be 1/2 x squared. So du is going to be x dx. Okay. So that makes it really easy to integrate, because now this is just equal to e to the u du, which is equal to e to the u, which is equal to e to the 1/2 x squared, of course. Okay. So when we go ahead and think of it in terms of this integral here, and we plug in the bounds and everything, we're going to have 0 to 2 of this part, and then 0 to 2 of this part. Okay. So let's call this, just so we have a link here, let's call this 1. And then we'll say that 1 is equal to, so we have x e to the x minus e to the x, okay, from 0 to 2, minus e to the 1/2 x squared from 0 to 2. So we plug in 2 there. So we have 2 to the e squared minus e squared. First term is going to be 0, and then we're going to have minus a negative 1. So plus 1. And then we're going to have, for this part, minus e to the 2, right? 4, and then times 1/2. And then e to the 0 will just be a 1. So we're going to have a plus 1 again, because we have minus a negative 1. So these ultimately will cancel out, and we'll just be left with 2. Okay. So most of this was just doing regular integration, but the key part is in how we set it up, right? Namely with the bounds here and where exactly we're cutting things off. So now let's say we want to do this in terms of x first. Well, again, we can't just integrate from 0 to 2. At this point right here, these 2 points, we're going from 0 to 2, but from any other point, we're only going from 0 to whatever this line is. So we have to cut off that region first. So this part right here, if we change this in terms of x, this is going to be x equals 2y. And then that'll allow us to do the x first. So if we do the integral from x equals 0 to x equals 2y, then that'll limit us to this region. And then the y parts, we won't need to worry about it. We can just do from 0 to 1. Okay. So it's like when we do it with the x, we're like putting ourselves on this slice. And then when we go from 0 to 1, we're like filling in the rest of the slice, right? Or going the other way, what we just did, we first, when we went from 1/2 x to 1, it's like we defined what slice we're on. And then when we went from 0 to 2, we filled in that slice. So it's like, that's when we like filled in this red part here. But of course, the actual integral itself would be 3-dimensional. But yeah, so let's go ahead and do it that way then. Okay. So we would do the integral from 0 to 2y of x squared e to the xy dx. And then we would do the integral from 0 to 1 for y. Okay. So if we're integrating with respect to x first, it's a little bit trickier. We got to do an integration by parts, and we're actually going to have to do it twice. But that's okay. We can handle that. I do think that in general, when you're thinking about which way to integrate, namely like do the x first or the y first, one of the ways is probably going to end up being easier. There will be some rare instances where when you do it one way, it's going to be impossible to get an answer. Like maybe you have something tricky like an e to the x squared that you can't actually do the integral of by hand. So you would have to flip the order and do it the other way first, and then that'll let you get to an answer. But in most cases, you'll be able to do it either way. Ultimately, it leads to the same thing. It just, one might be harder to calculate than the other. So anyway, so we'll go u is equal to x squared, du is 2x dx, dv is e to the xy dx, and then v is going to be 1 over y e to the x y. Okay, since y is the constant here. So again, I just want to look at the antiderivative first. So let me do it in a different color maybe, just to distinguish them. And then we'll worry about the bounds afterwards. So we have x squared over y, let's say, e to the xy, minus, we're going to have 1 over y, the integral of e to the xy times 2, let's put that 2 out here, times x dx. Okay, so then we do a second integration by parts here. So we let y equal x, So, or I guess we shouldn't use that variable, right? Let's we could just use a, I guess, and then dA is equal to dx, and then we'll say dB is e to the x y dx. So it's fine that we kept the y out here because it's a constant right now. And then b is equal to 1 over y e to the x y. Okay. So then this is going to be equal to x squared over y e to the xy. Whoops. E to the xy minus 2 over y times x over y e to the xy, a times b, minus, this is going to be b dA, so 1 over y e to the xy dx. So then finally, this is going to be x squared y e to the xy minus 2. This 2y gets multiplied by everything. Okay, 2x over y squared e to the xy minus 2 over y. When we integrate e to the xy, it's going to be 1 over y e to the xy. So this is going to be 2y cubed with all of that. Okay, so I really hope I didn't make a mistake here, because there's a lot that can go wrong here, of course. Okay, so let's just, go ahead and say, okay, then we're going to integrate this, or let's just say that we did integrate that. And let's just go ahead and plug in the bounds here. So this is going to be x equals 0. This is where I think writing out which variable you're putting the bounds in for explicitly is a little bit helpful here. So we'll just call this 2. I just like to label it so that this is easier to find later if you're looking at the notes. Okay. So we'll plug in the bounds here and then just really hope that everything is correct. I feel like there's just so much room for there being an error in this one. So this is going to be 4y squared over y. So we'll cancel one of those, e to the y, and then 2y times y, 2y squared, minus 4y over y squared. So that's going to be 4 over y ultimately, e to the 2y squared. Okay, so now I'm a little skeptical something went wrong because this will be hard to integrate. So I'll write this out and then I'll pause and go look for errors. So 2 over y cubed e, or maybe it's just not that hard and I'm just thinking it will be 2y squared. And then we don't want to forget about the 0 bound. These first two terms will just be 0, but this one is going to be, we're going to be plugging in a 1 here. It's going to be e to the 0, which is going to be 1 here, and there's no x term to make it 0, right? So minus a negative 2 over y cubed ultimately, so plus 2 over y cubed. And this is going to be the integral of this, of course. Should have had the integral from 0 to 1 of dy on the end here. Okay, so just looking over, I don't think that anything is wrong here, but I do think that this is one of those examples I was talking about where it is much more difficult to do it this way. Like I said, there might be some error in here, but ultimately I don't think it would change it too much to the point where this particularly this integral will be fine. This would be like a u sub, right? This first one here, but I don't know why my cursor's not showing up there, but anyway, so the second one would that's not an integral that has an elementary antiderivative, meaning like we can write it in terms of some normal functions. And I don't think the third one is either. The fourth one's fine, of course. So yeah, I think this is just an example of where one direction is significantly easier than the other direction. And that can be really hard to identify right away. So I mean, I'm just trying to think of like some advice for picking a direction, and I'm just like thinking of how to do it, and there's not a surefire way to know until you get to this point and see that it's going to be hard to go further. You know, you can kind of just try from the first step and see which of the first steps are easier. Like the first step here required integration by parts, whereas the first step on this one, you know, is much simpler. So that's kind of a good indication. Because if the first step is complicated, then usually the next step is going to be even more complicated, right? Not always, but that's just kind of how it is, because the first step is complicated because it produces this big long integral, or result rather, and then you're gonna have to integrate that. So yeah, that can make it, I guess that would be kind of a good indicator, is how complicated is the very first step. But in general, it can be tricky to know until you get to that certain point. And I did just throw it into Wolfram Alpha, just to be sure here, and it looks like the only error here is that I did miss this sign, right? This was a negative times a negative, so this would have been plus, which would make this plus and this minus. Okay, but ultimately it does not change the integral. It is not one that's possible to do by hand. So this is a way, an example where we'd be forced to do it in the other direction.